Okay, welcome to the keynote lecture of theoretical physics today. Today, the speaker is Professor Subir Sachdev. So Professor Subir Sachdev is Herschel Smith Professor of Physics at Harvard University. Professor Sachdev has named multiple seminal contributions to condensed matter physics, such as the theory of quantum critical phenomena and the deconfined phase transition, which is beyond the non-Dao theory, and the theory of spin liquid in quantum magnetism, and the theory of quantum matter without quasiparticles, just to name a few. Additionally, many of his contributions has been linked to the experiment, especially to understand the rich phase diagram in high TC superconductors. Professor Subir Sachdev has been awarded many awards and honors. For example, in 2018, he was awarded the Dirac Medal for his contributions towards understanding normal phases in strongly correlated systems. At the same year, he was awarded the Nas-Ansar Prize by APS for his seminal contributions to the theory of quantum phase transition, quantum magnetism, spin liquid, and for his leadership in the physics community. So today he will bring us a talk on the SYK model and its connection with the strange matter. So let's welcome.
Okay, there, the mic is working. Well, thank you very much for the kind introduction, and it's really a pleasure for me to be here at BIMSA for the first time. Really beautiful place, and thank you very much for your very kind hospitality. All right, so as the title says, I'm going to talk about the SYK model and introduce it for a general audience, and then hopefully get to some recent work where we've been trying to use insights that we've gained from the SYK model over several decades to resolve some long-standing questions in the study of correlated electron materials, and especially the very high temperature superconductors. All right, so what is the SYK model in its simplest form? So you imagine you have a bunch of quantum states labeled here by positions. Need not be positions. It could be any state that can, say, occupy a fermion. And so you occupy some fraction of them. And now you're going to have a Hamiltonian that's going to move the fermions around. And the most important feature is you don't allow the fermions to move one at a time. So this is sort of a fine-tuning, and we'll come back to addressing how that may be relevant or important for physical applications. But for now, just for the sake of solving a model, that you don't allow the fermions to move one at a time, but you do allow them to move by a two-body term. So for example, there can be a tunneling process where fermion on site 11 and 12 can move to site 5 and 14, and that's associated with some general complex number, which I call U 11, 12, 5, 14. So with every such two-body process, you can then associate some amplitude. So if I give you the list of these numbers, there's order n to the fourth of these numbers, then I fully specify, the full dynamics and Hilbert space of this model. There's a 2 to the n state, so it's far from being a random matrix because the number of, far from being a complete matrix because the number of matrix elements is about n to the fourth. But now this model is essentially unsolvable if you try to put it on a computer because of the very large size of the Hilbert space. But if you make one simple assumption that these U's are independent random numbers drawn from some ensemble, for convenience, we take zero average. So it's some ensemble of the U's, and the different U's are all independent of each other. So once you make that assumption, it turns out you can solve this problem in the large n limit. The solution involves some averaging, but for most properties, that averaging is not essential. because the system is really self-averaging in many observables, almost all observables. And so by averaging gives you an analytical tool for obtaining answers for rather complicated systems. All right, so that's really it. And now I can write down the Hamiltonian for a few mathematicians that might be here. You have these anti-commuting operators, C alpha and the emission conjugate. And from these fermion operators, you create this two-body Hamiltonian, and we're interested in the spectrum of this Hamiltonian as for some ensemble of numbers, U alpha, beta, gamma, delta, where we take them to have zero mean and mean square value U squared. You put this factor of n to the 3/2 to have a sensible large n limit, and you also have a conserved quantity that Hamiltonian, and that's the charge, and that will be between 0 and 1. All right, so this problem, as I've already claimed, is solvable the large, and in fact, the solution is related to actually this very nice gift I got yesterday from Qingyu Wang. So he can explain to you that this is some embroidery. This is supposed to be me, and I'm looking up at this little thing over there. So that little symbol is in fact how you solve the problem. It's work. Well, you just do a Feynman graph expansion of the self-energy of this problem. And so at order U squared, two graphs that you get. And then you take the graph and you over the ensemble of U alpha, beta, gamma, delta. So you see for this graph, there are 3 independent indices. And so you get a sum over, you get an n cubed from there. And there's an n to the 3/2 associated with each U in the Hamiltonian. So that was chosen just so that this becomes of order 1. On the other hand, this next graph, the alpha here has to equal the alpha out here because the different U are uncorrelated. And now you can see that gives you a factor of 1 over n. So in the large n limit, you can drop this graph. And in fact, you can show that in the end, in the large n limit, the only graphs that appear are exactly these graphs, just this one. But the Green's function here is a fully renormalized Green's function. So this is it. These are the very simple equations then for the solution of the SYK model in the large n limit. You have 2 functions of frequency or time, G and sigma, and they obey Dyson's equation. And this equation that's given by this one Feynman diagram. And there's a chemical potential, which is determined by fixing the charge Q. So I just have to give you the value of U, value of Q, and in principle, you can just go ahead and solve these equations. All right, equation so to solve, but you can determine, a lot has been learned about them over the years. We learned a few things already in '93, but more recently, we've learned much more of the structure of the solution of these equations through Kitaev and Maldacena and Stanford and others. There is some structure that's connected to quantum gravity, as I'll briefly mention at one part of my talk. Anyway, so let me just describe now the solution of these equations. As they are, as I said, they're already quite complicated. In addition to these equations, you also have certain analyticity constraint that just follow from the spectral representation that you have to make sure are satisfied. All right, so first of all, you can show that there can't be a gap solution quite easily. So any solution must be gapless. So then you make postulate, it's some power law, and then you run it through the equations, and you quickly find that the solution has to have this 1/2 exponent. Now, if this was a system with which would look like free fermions at low energy, then this exponent would be 1. That's the answer for free fermions with some constant density of states at the Fermi level. The fact it's not 1 tells you there are at least no C alpha quasiparticles, but doesn't rule out that there's some more other very complicated quasiparticles around. More carefully, if you're not at the particle hole symmetric point, then there's an asymmetry between positive and negative time corresponding to different densities of excitations of particles and holes. And that's characterized by this number E. And finally, there's a connection between E and the total charge. So this is the analog of the Luttinger theorem in Fermi liquid theory, where there's a connection between the Fermi wave vector and the total charge. Here you have another example of a compressible Fermi system, and the Luttinger type arguments still apply and give you this relationship between E and Q in terms of this intermediate variable. Okay, so those are things that, after some amount of work, you can determine slowly over the years. There's further properties, however, I want to emphasize, which are now understood due to an emergent time parameterization symmetry that the low energy theory has. So the low energy theory of these equations and the corresponding action is 0 plus 1 space-time dimensions and has an emergent time parameterization and conformal symmetry. So what are some of the consequences? Well, one is that if you define some appropriate relaxation time to some perturbation at a frequency omega, then you find what's called Planckian dynamics, which means that these relaxation times are just determined by temperature and frequency where this function f is some function that depends on exactly how you define tau. But more importantly, the value u, the interaction strength, simply doesn't appear. So this is another consequence of not having quasiparticles, because if you had quasiparticles, there'd be a Boltzmann-like equation. And you know that the relaxation time in a Boltzmann equations depends on the collision term, which is proportional to u squared. So, but here u just drops out, and hence this remarkable universal Planckian dynamics. I mean, this kind of observations of such Planckian behavior were very much apparent in some experiments on the high temperature superconductors already in the early 90s. And it was a motivation to find a toy model of that behavior that really led us to think about what's now called the SYK model, or the early version of the SY model at that time. And so we were very happy to see behavior like this emerge from this very simple model of interacting electrons. And so here, for example, one consequence of that, if you look at the Green's function at finite temperature, the power law singularities that I mentioned earlier at 0 temperature get rounded out, and the scale of the rounding is again just temperature. Okay, so the other important property I want to emphasize, understood from the solution of these integral differential equations, is the 0 temperature entropy. So this problem, compute the thermodynamic entropy from the partition function, and then take this very special limit where you look at the entropy per particle and you send n to infinity first before you send temperature to 0. And you get a value that's non-zero. And cute. But a very important point, and this really was the model to show this, that you get a 0 temperature entropy without exponential ground state degeneracy. So, I mean, there were other models earlier, like Pauling's ice model or very fine-tuned models, usually classical, which have exact ground state degeneracy and hence give you finite entropy density. But here, and here this order of limit is extremely important, you get 0 temperature entropy without any exponential ground state degeneracy. And if you look at the actual many-body density of states, here's some recent numerical results. The whole density of states has a prefactor, which is exactly this number, hence telling you that but there's no degeneracy. The level spacing here between different levels is exponentially small, and hence the density of states is exponentially large. Today we also know that there's an envelope, some smooth function, which actually vanishes at the bottom. But in any case, none of the states down here have any large significant degeneracy at all. So this observation, bizarre to us because it really never been any model that had displayed behavior. And certainly it wasn't related to any observation in the cuprates or any condensed matter system I knew of. But over time, it's become clear that it's precisely this feature that's actually just the ticket to understand some basic issues in black hole physics. So I'll just mention that very briefly. This talk is really about strange metal, but given the talk of Edward Witten today, and also I think Alexei will say much more about this tomorrow. But let me just quickly mention the connection to black hole physics and then return to patient. So if you were very naive, you would try to evaluate the partition function of a black hole by just taking the Einstein-Maxwell action for 3+1 dimensional gravity plus electromagnetism and doing the integral over the metric and the gauge field in a black hole background. So that's, of course, impossible even today, or even not even clear that means anything. But it turns out that in the low energy limit or the low temperature limit of such a black hole, there is a way to define this in a rather precise way. So what happens in the low temperature limit of such a black hole this is a black hole with a net charge Q, is that there's a dimensional reduction. So this is an action in 3 space and 1 time dimension. There's the 2 angular directions x, there's a radial direction zeta, and there's time tau. So in this picture, I've only shown zeta and tau. Tau is imaginary time, in which case the metric has the shape of a cigar, which ends at the horizon. So it turns out the dominant fluctuations are only along the zeta tau directions. You can ignore the angular direction. Ignore the angular direction x, you can reduce this to a path integral of 1 plus 1 dimensional quantum gravity called JT gravity, modulo a prefactor, and the prefactor is the area of the horizon at 0 temperature. So as we know, once you have a black hole horizon, there's a finite entropy. Charged black hole, it turns out to have a finite area even at 0 temperature. And so this is really a close connection then to the property of the S/K model. Here again, from the Bekenstein-Hawking formula, you're getting an entropy overall prefactor that's coming from the 0 temperature limit. But now the remarkable thing is that you can take this path integral over 2 plus 1 dimensional gravity and actually perform it essentially exactly. So it turns out you can reduce this path integral 1 plus 1 because of the simplicity of 1 plus 1 dimensional gravity to a path integral in 0 plus 1 dimension. It's only dominated by the boundary of this low dimensional space. And really remarkably, this path integral, this action that you get here, is exactly the action you would get from the low temperature limit of the action corresponding to the equations I showed you earlier for the S/K model. You get the same path integral starting from this random model of randomly interacting fermions as you do from just dimensionally reducing 3 plus 1 dimensional Einstein gravity in the background of a charged black hole. All right, so this path integral can be done both for boxes and for the case of the latest result. There's the exponentially large prefactor, that's the Bekenstein-Hawking term, which is energy independent. And now we know the energy dependence, the density of states, this function f of E that I mentioned earlier, again, given by the same A0 and various constants. And most recently, through some beautiful work of Luca, Elias, and others, the prefactor here has also been determined. The prefactor depends upon the actual particle content of the quantum field theory and is not as universal as this term over here. All right. One thing notable about this is that unlike theories which have low energy supersymmetry, there is no degeneracy. Whereas in the BPS states in supersymmetric black holes, always realize this, this density of states by a delta function at zero energy corresponding to the large entropy, corresponding degeneracy of these BPS states. And so here's a fanciful picture. I'm not claiming that there's actually an SYK model inside a black hole, but it captures, it's a sequence in modern of certain low energy properties from the point of outside observer. Okay. All right, so now let me come back down to earth and talk about connected systems. So my motivation is strange metals, and I've shown you how the SYK model realizes a key property of strange metal, which is this Planckian relaxation time. But it's still a 0 plus 1 dimensional model. So it turned out to be just what we needed to describe charged black holes, but it can't be directly applied to any condensed matter system. So let me begin by taking this a small step in the beginning and asking, are there other simple models in 2 plus 1 dimensions that have Planckian dynamics? So the simplest model is just the Ising model. So you take a quantum Ising model of some qubits, the operators Z and X. There's this ferromagnetic interaction between the qubits that gives you a ferromagnetic ground state at G equals 0. They're shown over here. So there's a twofold degeneracy in the ground state. All spins can be up or all spins can be down. But as you tune the coupling G, eventually at G goes to infinity, the symmetry will be restored, and you'll have all the spins pointing in the positive X direction. So we know now that there's a single quantum phase transition in this model in any dimension at some critical coupling GC. And we are particularly interested in what happens here. Now, if you look at the dynamics of these spins, either in this phase or that phase, you find that they're amenable to some quasiparticle description. The quasiparticles on this side are little domain walls of reverse spins, and here, so there are spins that flip from plus x to minus x. But it turns out, and this is only true plus 1 dimension, there's something very interesting at G. In particular, the quasiparticle description breaks down. So what we know is that, in fact, in 2 plus 1 dimension, this critical point is described by the Wilson-Fisher conformal field theory, which is just a 5-fold field theory. And this flows to a universal Wilson-Fisher criticality right at G equals GC. And if you now interpret the properties of this field theory, which has usually been studied, at least in condensed matter, as a statistical mechanical theory in 3 dimensions, now let's think of it as a quantum theory in 2 plus 1 dimension at finite temperature. And then it turns out that the quantum critical dynamics of this point describes the behavior in the so-called quantum critical fan, where temperature is a more important perturbation than the tuning parameter G. And in this quantum critical fan, you indeed get Planckian dynamics with I mentioned for various relaxation times earlier, where the characteristic time is essentially temperature itself, and not the value of G or J or anything else. All right. For studying the behavior of such phase transitions and applying them to some real material. Now, this Ising spins itself had only recently been realized in a number of cold atom and but again, I apply the confidence something like the cuprate superconductor because those are that are metals. They have mobile electrons with Fermi surfaces. This is an insulator. It doesn't have any mobile fermions, and so simply doesn't apply to any conducting system. So we have two toy models now. We have the SYK model, which has lots of fermions, but they're in 0 + 1 dimension. And we have the Ising model, which is certainly in the right dimension, but it doesn't have fermions, which can carry charge and give you superconductivity or strange metal behavior. So we have to now combine them, and that's really the rest of my talk. So let me then now turn from the quantum phase transition of the Ising model to a quantum phase transition of metals. All right, so why would I want to study quantum phase transition of metals? So now let me finally get, talk about some real physics here, about a real material, yttrium-barium copper-oxide. This is the famous phase function of electron density and temperature. So here, this is density away from 1 electron per site as measured on a single square lattice. So we assume for all of this discussion that the different layers of copper and oxygen are decoupled. It's going to talk about of a single layer. And just focus on the copper. Now, when you have exactly 1 per site, it's an insulator, as on a chipboard. And some electrons, you have the remarkable phenomenon of superconductivity. So this is still, discovered in 1980. It's still the very best superconductor until the applications, but also for the deep theoretical question it raises for theoretical physicists. So of course, the big mystery in these materials is why is TC so high? But really, I want to focus on what happens above TC for the simple reason that you have no hope of computing TC unless you know what the other state you're coming from is. And the state you're coming from is called the strange metal, and I'll describe some of its strange metal properties. And that immediately means that you can't really apply the usual Bardeen-Cooper-Schiffer theory to understand this superconductor, because the Bardeen-Cooper-Schiffer theory is really a theory. It has two ingredients, which then condense. That part everyone believes is also in this case. It describes the condensation as an instability of a Fermi liquid. A Fermi liquid is an ordinary metal which has many properties not seen here at the highest TCs. So, the first property of BCS theory is fine. The fact that BCS theory relies on an instability of a Fermi liquid means you can't really apply it. Okay, so what are some of the strange properties? So I'm sure you have all heard about the linear interior resistivity. This is unlike some metal like copper, where over this low temperature range, you typically have a T² dependence. Now, there are many models proposed of the linear interior resistivity. A somewhat more subtle and more difficult to explain model is the frequency dependence of the conductivity. So this is measured by reflectivity measurement. You send in infrared light, you measure the reflectivity, from which you can read off the real and imaginary parts of the conductivity. So here, if I just imagine this quantity m star of omega and tau of omega are just constants as a function of frequency, then I have the famous Drude formula for the frequency dependence of conductivity, just given by thinking of electrons scattering randomly of impurities. Now, what you find here is that both tau of omega and m star of omega are far from frequency independent. And in particular, if you look at the absolute value of sigma, it has a very slow tail falling off as 1 over omega, and its phase is also strangely temperature dependent. So this is really kind of signature property that any theory. All right, so how are we going to explain it? Well, let me just set up the framework. In addition to the strange metal, which is mysterious, if you look at the metallic states on either side of the strange metal, they're a little bit easier to understand. So on the high, you have an, and low doping side, you have what's called a pseudo gap, which all, an understanding is due to. These are metals in which quasiparticles exist, and many of their properties are conventional. So perhaps the way you want to think about it is that the fundamental thing going on here is some phase transition between two metals, and in between is the strange metal. So let's take that scenario. So sorry, I forgot to show this. So the ordinary metal in particular has a well-defined Fermi surface, which is exactly where you expect it if you just treated the electrons as free electrons. So this is the boundary between occupied states in the center and unoccupied states on the outside. Where the Fermi surface seems to be modified. I'll mention various models and that can happen in a few minutes. But now the idea that we're going to view the strange metal as a property of some t equals 0 quantum phase transition involves the change in the Fermi surface of the electron. Now, of course, at 0 temperature, there's a superconductor. But for the moment, we're going to view the superconductor as an annoyance. That's something that's hiding the underlying change that happens at higher energies, which is the change in the nature of the Fermi surface and some phase transition in this metallic system. So just for a while, at least certainly for the rest of this talk, since I won't say more about superconductivity, we'll take this very simplified phase diagram. We propose that there is some actual critical point between which there's a phase transition at 0 temperature between two different conducting system metals. One is the conventional Fermi liquid, and other is a more complicated Fermi liquid in some sense, which I'll say a few words about in a minute. So depending on the particular model you choose for this pseudo-gap metal, you get different theories to describe this change in the Fermi surface. But they have some common features. First of all, they do have this Fermi surface, which is the Fermi surface here, where this on the overdoped side. But they, in addition to the Fermi surface, a scalar field phi. This phase transition is described by the condensation of this field phi. So that we view S as a mass of this field, and when S is negative, the field condenses. And that leads, because there's a Yukawa G in phi and the Fermi surface. All right, so what are specific models of this? So for example, a Fermi surface people have applied to not so much the cuprates, but other materials. So here, say you have a square lattice. Has the lattice has symmetry of the width direction is the same as the width in that direction. But because of some electron interaction, it likes to reduce its symmetry. It wants to become longer in the y direction than the x direction. And so now there's an Ising parameter. That's why that produces an Ising field phi. And so this can have, if it's positive, say the Fermi surface distorts direction, and it distorts in the x direction. So this is an Ising nematic critical point, and it's a paradigmatic example which has been studied in great detail. And I'll say a few words about its properties shortly. Another type of transition, which also involves symmetry breaking, is, say, antiferromagnetism. So, which is really closer in spirit to what's happening in the cuprates, at least at very low doping, although not near where you get the highest TCs. You have antiferromagnetism, where the spins are aligning in opposite directions on the two sublattices. Now, once these spins align in this manner, the Fermi surface splits apart into electron and hole pockets. I won't go through the details. And this is not so far from what you see in the pseudogap, but except that in the cuprates anyway, the antiferromagnetism doesn't last all the way up to where the quantum critical point might reasonably be. So again, I would hesitate to apply this to the whole dope cuprates. So this is also a very similar type of theory. Now you have a scalar, a field that has three components corresponding to the components of this orientation of the magnetism. Okay, so this has also been studied a great deal, which is what I call type 2. And finally, is the most relevant for the cuprates, a bit more exotic. You get a reconstruction of the Fermi surface without broken symmetry, and that involves certain spin liquid character. So you have a coexistence of a spin liquid and a Fermi surface in a state we call FL star. And in this case, this field phi becomes a Higgs field, and there are also certain gauge fields representing the topological order. So in fact, I'm going to talk about this particular theory in more detail in a talk at Tsinghua on Thursday, if you're interested. Anyway, so these are the three types of theories you might want to study and understand what their properties are. And there's been a huge effort in the community studying exactly these theories over the past 2 or 3 decades. Okay, so now let me summarize some of the properties that have been learned about this theory of coupled bosons and fermions, describing some change in the nature of the Fermi surface in a metal. All right, so let's take the type 1, which is the first one, where you just have an Ising order parameter. I talked about distortion of the Fermi surface. Equally, I talked about fermionitism, will be essentially the same theory. So your first guess from everything you learn in graduate school is you have a broken symmetry, an Ising broken symmetry, just described by 5-fold field theory. And this is the dominant low energy excitation in the phase transition. However, here there's another set of excitations, which is the Fermi surface. So there's a zero energy excitations on this line in momentum space. And now you have to couple them together. All right, so this is the theory that's been studied a great deal by Hertz in 1976. And he argued already then that the coupling G is extremely important, and it changes the universality class of the theory away from the Wilson-Fisher fixed point, which would describe the scalar part of it. Okay, so Hertz didn't really get, I mean, everything in his paper is correct, but he didn't fully understand the subtleties of this theory, especially in 2 dimensions. So that's been understood more recently. And one way to understand it is to take this theory and put it through the same framework that we put the SYK model through. So in the SYK model, we put in some interaction that was a random function of some flavor space. So let's imagine taking this theory and putting a flavor on everything while maintaining translational invariance and taking this coupling G and giving it some indices. And imagining this coupling is random in flavor space. So this gives what's called the Yukawa SYK model, at least in the condensed matter community, and also in the zero-dimensional limit has been studied a great deal. So from these, in this type of large N limit, you can get the SYK type equation, and this are basically the Migdal-Eliashberg equations made self-consistent between the self-energy of the fermions and the self-energy of the bosons, and D here is the boson Green's function. So you have to solve these 2 equations, which actually in 2 dimensions turns out to be soluble. And in fact, yeah, so there's the equation written out explicitly. Now they're far more complicated than the SYK equation because the self-energy is a function of both frequency and momentum, since you have translational symmetry. But it turns out you can at least understand the low energy properties at the quantum critical point essentially exactly, or at least in this context of these equations. And the answer was already given by Patrick Lee in 1989. What you find then is the self-energy is some power law of frequency. In this case, it's 2/3 rather than 1/2 was the case in the SYK model. This is the self-energy of the fermions. And furthermore, this type of self-energy means 2 things. One, that the Fermi surface doesn't disappear. There's still a Fermi surface, but because the self-energy becomes larger than omega, that in fact there are no quasiparticles. So there are these very complicated set of excitations that don't have a quasiparticle description, but they're sharp in momentum space, but broad in energy space. And the entropy vanishes at 0 temperature, so that's perfectly fine. Okay, so that seems exciting. It looks like we're getting close to some realistic description of the strange metal, and many people have claimed so over the years. So now let's look at the actual properties that I mentioned earlier, the optical conductivity. So if you evaluate these graphs, which was looked at again by Patrick Lee's group way back when, they concluded that there is some not quite linear anti-resistivity, but almost linear, and a tail in the conductivity, which looked sort of like what was being measured in the optical conductivity experiments. Okay, now we know that both of these results are actually incorrect, and through rather subtle reasons. We started realizing this actually from the connections to holography, where it was obvious these results couldn't be correct. The point really is that what these calculations ignore is what's called a drag effect. Here we are imagining that it's the fermions that are scattering of the bosons, and we're taking that to be the dominant mechanism for transport. But the bosons will eventually give their momentum back to the fermions. In fact, the interaction between fermions and bosons is so strong that you cannot think of them as independent degrees of freedom. So you really have to look at the collective fermion-Bose system as some quantum fluid, which is something, in some limits you describe in dual holographic theories. But in the end, you don't need holography. If you evaluate these graphs carefully enough, as was done, for example, with my former student, How You Go, you can show that this coefficient C is 0, and the conductivity is, in fact, the conductivity of a perfect metal. All right, so to summarize then, and this turns out to be true for all 3 classes, this is the framework in which many people, including us, have been studying, strange metal behavior. Encouragingly, we found that the 0 temperature behavior is indeed a system without quasiparticles. It's a non-Fermi liquid where if you looked at certain dynamical processes, you will find Planckian type relaxation, just like in the SYK model. But if you look at transport properties, which is really the dominant properties that are defining the strange metal, it's not a strange metal at all. It's in fact a perfect metal due to this extreme drag phenomenon. All right, so these were conclusions that were becoming very clear to us a few years ago. And so we started to think about, well, how are you going to resolve all this? Seems like the most natural model for a strange metal doesn't work at all. Well, so at this point, so you have to, the key is that you have to find a way to relax the momentum of this model, which has perfect translational symmetry. Now, you say you have a lattice, and the lattice means its translational symmetry is broken, but it's broken in a way that involves what's called large momentum transfer processes, the so-called UMPLA processes. that relaxed momentum, and they're exponentially rare in any of the models that we are considering. It requires fine-tuning for Umklapp to be there. So really, you have to worry about spatial disorder and take a system which is slightly inhomogeneous. Now, this shouldn't be a surprise. I mean, I don't know why people were reluctant to do this over the years. Even in the theory of ordinary metals, disorder is essential. The Drude theory is due to disorder. Then the subsequent theory of localization by Anderson and interaction correction by Altshuler-Arnov is all dependent upon having weak disorder, and it's quite important. In the Drude theory, but you have in ordinary metals often, if they're clean enough, something called Matheson's law, which says that you look at the effects of disorder, you look at the effect of interaction, and just add them up. And that gives you the total relaxation rate. You can't do that near quantum critical points. So it turns out, and we are now going, we think we are starting to understand all of this. Key is to treat disordered interactions self-consistently in exactly the way they're treated self-consistently in the SYK. And amazingly, once you do that, in what we are calling the two-dimensional Yukawa SYK model, there's a universal theory. In other words, for the three different classes of quantum phase transition, you get the same theory. Okay, so this I'll present some recent results with various people. I've already mentioned Hayu Go, my former student, and another former student, Avishkar Patel, who's been doing extensive Monte Carlo results studies, which seem to be entirely consistent with the SY-K-type analysis I'm going to present. All right, so here's the theory we were studying earlier. So I have about, how much time do I have? About 10 minutes maybe? Okay, but that's with questions, I suppose, so I'll try to leave a few minutes for questions. All right, so this is the theory. You have a Fermi surface. You have this Ising model, if you wish, described by the Wilson-Fisher theory, and you have a Yukawa coupling between them. All right, so let's put in some randomness. Now, the way you normally put in randomness in the theory of metals is by putting a random potential for the fermions. And this leads to elastic scattering of fermions. It's the basis of the Drude theory. And if the systems are disordered enough, there's localization. And this could be important in many materials. Now here, it turns out that, especially in two dimensions, the localization effect is rather weak for weak disorder. And we believe this is not the key effect, although it has to be included in the theory. There's another much more important effect, and that's the so-called Harris disorder. That is, remember I told you that the quantum critical point is determined by where S, say, changes sign in mean field theory. But it could be that the value of S is different at different points in space. This region could be on one side of the critical point, this region could be the other side of the critical point. And that disorder is invariably near any phase transition the most important thing that you have to worry about. And there's a very important inequality, various exponents have to satisfy. And really, it's no surprise, right, really, that you do have to worry about this Harris disorder. Okay, so this is the term you really have to keep. It's much more relevant than any localization effect on the fermions. It's the mass term for the bosons, not the mass term for the fermions. Okay, but it's so relevant that it's actually quite hard to treat. If you try to treat it by the SYK tricks, you don't get any meaningful answer. So we hit upon the following idea. We said, which has now been checked numerically, but for now, let me just present our thought process. We're going to rescale phi in a way that this becomes spatially independent. And that, in a sense, in other words, we're going to some eigenmodes, which are the eigenmodes of the random mass. And we would think that would make sense as long as these eigenmodes are extended. If they start to localize, well, then you're in trouble. But if they're extended, then you rescale phi, and that's going to induce disorder everywhere else phi appears. And the most important place it will induce disorder is in the coupling. So this is what I want to study then. you put the randomness not in the mass, but in the Yukawa coupling, the spatial randomness. Okay, and now you just go ahead and put in indices and take a large N limit to begin with to solve this theory. Okay, so this is what we propose to do. And then the SYK equations, before I get to that, so I think I already mentioned this. So we apply it in the self-averaging model. It should be applicable as long as these phi bosonic eigenmodes are extended. All right, so these are now the extension of the SYK equations to the case of having one fermion, one boson, a spatially uniform coupling and a spatially random coupling in blue. So you can put this on a computer and solve it. This is still a bit too complicated to solve completely, but you can either do perturbation theory for small g, or you can solve them completely at g equals 0 when the self-energies are still only frequency independent. But everything seems to hang together. So among the things you get is actually exactly what you observe. You find that the Green's functions have this linear frequency dependence, which is the so-called marginal Fermi-liquid dependence. And it comes from both the spatially uniform and the spatially random components. But the optical conductivity only depends on the spatially random component, because the spatially uniform component cancels due to the drag effect. In fact, the frequency and dependence of the effective mass and the transport are exactly what's observed. So in fact, recently, we've done a full solution and tried to compare with data. So for example, you have this linear T-resistivity in this region over, in this region over here, the white region. And that's half of the white region. That's the overdoped side, where linear T-resistivity is in red. Here's the resistance at the quantum critical point and what it looks like away from the quantum critical point in the ordinary metal. Here's the optical conductivity data. Here's our calculations with essentially, as a function of temperature and frequency, really matching the data very well. This is the tau of omega as a function of frequency and temperature. So here, in fact, it was experimentally observed this famous, you can see this famous collapse of tau as a function of frequency and temperature to only a function of temperature and frequency of this form. And that's exactly what you see in the experiments. And that's roughly what comes out of this computation too. All right, so that's, I guess I should, yeah, okay, I finished earlier than I said. All right, so that's the story. And I think, so we take this spatially inhomogeneous Yukawa SYK model and just turn the crank on its properties from everything we learned on the zero-dimensional SYK model, and it seems to capture really a significant fraction of the data that's available. But there is one more piece of the data that I want to now mention, which is subject of a lot of recent studies. So let me just mention that, then I'll conclude. So this is this famous foot. Okay, so this is a lower temperature study, in this case by Nigel Hussey's group of lanthanum, strontium, copper oxide. And this is the fan, quantum critical fan that I've been trying to describe, where this will have linear T-resistivity. So that's one. If the resistivity is, if the color is blue, then you have a T squared. Now in this material, they've actually suppressed superconductivity by applying a magnetic field. This is where TC was. And when they look within the superconducting region, they find that rather than coming to a point, it seems to have this famous foot. And this is also seen in many other materials. So it seems like the linear T-resistivity has this fan-like region, which I've already studied, but it also seems to have an extend on the overdoped sides to some region where the resistivity seems to be almost linear. So what is this due to? Well, we have several recent papers on it, and we're pretty confident where that's going, but I'm not going to go into that for lack of time. But let me just mention the following. So the theory that I presented so far, where I just do some self-averaging theory of bosons and fermions, the whole procedure only makes sense. Self-averagingness only makes sense if the eigenstates of the fermions and bosonic modes are all extended. They just some random functions over all of space without any particular localization. And because they're in then extended states, there is a self-averaging, and then you can use this kind of average SYK procedure. But what happens here is that, remember I told you this boson mass is strongly relevant. So it turns out that eventually that boson mass has to be accounted for exactly, a little more, much more carefully than we have so far. And what happens is that the bosons localize. So you get these overdamped modes of very short, very small size, tens of lattice spacings or smaller, which develop at low temperatures in our numerics, and also we believe in the experiments. And it's the bosonic modes that are localizing, not the fermions. So that's kind of unusual from a condensed matter point of view. People always talk about fermion localization, but in fact, it's the boson localization that's most important here. Anyway, so that's work in progress, and we're pretty excited of being able to explain this feature too. All right, so conclude. So the SYK model is a model of many particle entanglement. It leads to a state of matter that has no quasiparticle-like excitations. I guess I didn't really explain this. The fact that it has a finite zero temperature entropy means there's so many states at low energy that's impossible to find a quasiparticle decomposition of all such states. Quite remarkably, precisely this toy model in 0+1 dimensions is in fact dual to the low energy theory of charged black holes in 3+1 dimensions without low energy supersymmetry. There's a supersymmetric version of the SYK model that captures the supersymmetric case that, you can talk to Luca Aliasio for more about that. Then I went to 2+1 dimension and talked about quantum phase transition of qubits. It's certainly very well understood, but not directly relevant to any conducting system. And I discussed the quantum phase transition of metal, where you find that there's a breakdown of fermionic quasiparticles. So that's similar to the SYK model. But because of the presence of translational symmetry at low energies, the transport is actually completely perfect. It's not strange. And finally, we put in some inhomogeneity on this theory and apply the tricks that we learned from over here. Everything seems to be falling into place. So thank you.
Questions? Thank you.
Oh, yeah, I can hear you.
Yeah. My question is, what of the bosonic field in realistic superconductor theories?
Well, that's a great question on this boson field phi. I mean, I think it depends what material you're talking about. So if you're talking about the pnictides, then it's almost certainly some antiferromagnetism. Because in the pnictides, you do see the antiferromagnetism coming all the way to optimal doping. But in the whole dope cuprates, like I showed over here in the very beginning. Oh, no, there it is. Okay. So if I take antiferromagnetism in the field phi, here's the antiferromagnetism, whereas the quantum critical point is somewhere here. Okay. So it's just not reasonable to say it's antiferromagnetism here, but it could be in some other materials, some less correlated material. So this is the material with the highest TC. So maybe your question is, what is it here? Well, so that's what I will discuss in my talk in Tsinghua on Thursday. Where did it go? Yeah. So I believe it's this field phi. Well, okay. So our theory for the pseudo gap is what happens is that some of the electrons localize into a spin liquid, whereas others form a Fermi surface. And exactly how you describe it is a bit subtle. That's what my talk on Thursday will be about. But in the end, because there's a spin liquid, then there are some fractionalized excitations, okay, in the spin liquid. Now, it turns out that so there are these fractionalized, in fact, and you can always set it up so that there are fermionic excitations in the spin liquid which carry gauge charges. But you also have the physical electron around, which form the Fermi surface. And it turns out the relevant field phi is a composite of these two. It's an anion that has both the physical charge of the electron and the gauge charge of the fractionless fermion. So it's like a Higgs field. It's a composite Higgs field with a complicated set of charges. So you get some, in addition to the Yukawa coupling, there's a gauge field that you have to worry about. All right, so that sounds very complicated, and you might be ready to give up. But the remarkable thing is, once you go to the random system, none of that matters. It doesn't matter whether there's a gauge field or not. It's a Higgs field or an autoparameter, broken symmetry, no broken symmetry. You get basically the same theory. Yeah.
So you applies this bosonic field phi
Yeah.
to the randomness, and you have some problem.
Well, so yes and no. I mean, so first of all, yeah, let me put the theory. Yeah, so exactly. Let's see. Yeah, so you're asking about rescaling phi. Yeah. So that would also induce some correction to the gradient term, which will also become spatially dependent. Yes. So in the approximation we are solving it here, that's not as important. You can put it in the equation; it doesn't do much. However, in the limit where this G prime or S becomes very large, then there is a renormalization of the gradient term. And that's precisely the effect that comes into understanding the foot. Okay, so to understand this boson localization, you also have to understand the renormalization of the gradient term. I didn't talk about it, but that's the part I skipped. So there's a strong disorder. You can take another limit where there's no self-averaging, where all the bosonic excitations are localized. And then you can do a strong disorder RG. And this RG is very similar to the RG that Daniel Fisher developed for the transfer-spherizing model. You get a very similar set of RG equations where you do get a renormalization of the gradient term. So you're absolutely right, it's important, but we claim that it's not so important up here, which is what's described by the SYK equations. But down here, where you have, here you have complete breakdown of self-averaging, you have localization, you really have to treat the disorder exactly. And there's really very few analytical methods. We've done a lot of numerical work in that regime. Yeah.
SYK is explicit, but it is explicit. It's implicit topic.
Yeah, so that's kind of what you learn when you're doing the theory of the quantum phase transition. Right, so so here's, let's go to the pure theory, this theory, without any disorder. You could, away from the quantum critical point, you could integrate out phi and get some quartic term for the fermions. And that leads to what I call the Fermi liquid renormalization. So that gives you some Fermi liquid corrections. But what we are ignoring those Fermi liquid corrections because we are interested in the properties near the phase transition where phi is becoming long range. So there's one channel that's becoming very long range in the fermion interactions near the phase transition. And we take that channel and we write it in terms of a local scalar, because that's what you're taught, how you treat quantum phase transitions. You want to take whatever the long range interaction you have and make it a local field. And that's what we're doing. It won't do much, no. Not near this quantum phase. I mean, you'll get Fermi liquid theory. So the thing about, yes, let me answer that why. Another way to think about, so I mentioned at the very beginning of my talk, the most important thing about the SYK model, you don't have single particle hopping. This model has lots of single particle hopping. It has a whole Fermi surface. This E of K is the largest thing in the problem. So it's got a Fermi surface. The fermions are moving around merrily. So the quartic interactions don't do much. They will just give you Fermi liquid renormalizations. it's only when you get the scalar field, which is near either a Higgs transition or a symmetry breaking transition, that you start to get Planckian physics, which we are now solving by some tricks we learned from the SYK model. I mean, really, in the end, everything I'm saying in the end could have been done without anybody ever mentioning SYK. But that's not the way things developed. I mean, I can just say the same thing about black holes too. The understanding of black hole, the cinch density of state correct, could have been done without SYK at any stage. But just having that example around was very important for the development of the theory.
Special role in finding this function.
The randomness in what?
Of the V term.
Not in, it does, I guess so. This V term just leads to some Drude scattering, which is important. You know, this term here, there's an elastic scattering term that comes from that. And so very importantly, I guess I didn't write this down. Yeah, there is one much more important effect, which I didn't mention, which is that the boson, if you take the clean limit, the boson has this Landau damping factor. Because of the V, the Q is not there. And this is, in fact, the reason for the universality. Once you have the V term, all the Fermi surfaces get a little broad. And so the different cases look just like each other. And the boson has a diffusive form at low frequency for every case because of the V term. So I didn't mention that, but that's quite important. Yeah.
The information, this delta S that you turn on in your model, it's kind of similar to the Ising model.
Yeah. Yes.
The sort of Ising model was studied in couple of perturbation theory.
Yes. Yeah.
Fixed point.
Right.
Do you think you can study this model in perturbation theory using the data that we know about the Sachdev-Ye-Kitaev critical point?
I don't think so. This is much more relevant. It flows to, in fact, the final fix. So in that case, the Ising model with random mass, you, at least in the epsilon expansion, you get a fixed point at fixed finite disorder. Here at low enough temperatures, you know, the Daniel Fisher style RG shows you actually flow to infinite disorder. So the fixed point, ultimately, if you really go down to low temperatures, then there's like a Griffiths phase, and it's described by infinite disorder fixed point. So which is quite far from the SYK limit, but you know, the system displays both regimes, and now we are starting to understand how they're all connected to each other. Yes. In fact, you're right. So there's the Yukawa SYK. If you take the 0 + 1 dimensional limit of this, that is in fact the first place the Yukawa SYK model appeared. Is my only paper with Juan Maldacena and David Egarto and my student Bienbo Fu. So there's a supersymmetric SYK, and the way it's solved is precisely by introducing a boson there, and that also has a 3-index random term. So that was the first place what you might call the Yukawa SYK model appeared. Subsequently, many people pointed out you don't need supersymmetry. You get the same physics even when you lose at least n = 2 is special, but if you had n = 1 supersymmetry, there's really no special features, and you can get the same kind of phase even without supersymmetry, which is what I'm using here. Yeah, so, right. So if you have supersymmetry, certain exponents are fixed to certain values. But the fact that you have Planckian behavior and no quasiparticles, it's also true without supersymmetry.
Thanks for the question. Thanks to Professor Sachdev.